All right. So we were studying exception architecture, and in exception architecture, I told it is an improved or better architecture than Inception V3, because Inception V3 is having some drawbacks that we will see, and then exception do have changes in its approach. The idea is to reduce the complexity and to increase the performance for classification task. Okay, so in Inception, which was a improved pre-trained model from VGG 16 and 19. Okay. In VGG 16, okay, and 19, what you have saw that the CNN convolution, then pooling, then convolution. That means you created the blocks, and in this particular blocks you were using all the layers in a sequence. Okay, fine. We can also make such architectures from our side, but the importance lies in this pre-trained architecture is they are having weights of ImageNet data set, and in ImageNet data set we are having millions of images over which these models are being trained. So they have a good knowledge of how to treat images. So in transfer learning, in this particular workshop, from the starting, and we are at this stage, we have used the weights, okay, of these models, and that's the advantage. Okay, that's the advantage. The reason is, if you start from scratch, because the people obviously here they will be asking, we want to make our own architecture, and obviously in that particular case you have to start from scratch. You have to make your own CNN layers. All right, you can, it's not been clear what you will be going to do. Okay, you have learned these architectures from me. Okay, and some changes we incorporated in these architectures, that is attention mechanism, that's what we have added in these architectures. Okay, and the performance boost which is being expected, we have seen that the results are better. Now the thing is, if you want to start from scratch, you want to make your own architectures, you will be after learning all these things, you will just build convolution, pooling, something like that will make an architecture. Okay, in Inception V3 you learned that we can organize the layers in parallel also. So instead of just all the sequence, you can organize something in parallel. That also you can do. In Inception, you have also learned that, sir, we can have asymmetric convolutions, like we can have 3 cross 1 and 1 cross 3, something like that we can do. Because you have performed the factorization here. Okay. And in case of factorization, you have simplified 5 cross 5 to 3 cross 3. And then further 3 cross 3, you have simplified to 1 cross 3 and 3 cross 1. So now you are having this knowledge. Okay. So something you can make from your side. Okay. But the point is, they are already existing in a sequential way. VGG 16 and 19 is existing. In a parallel way, Inception is existing. And exception, this architecture, what happened in this architecture? You have been told that we perform depth-wise convolution. In depth-wise convolution, it's been said that you have to perform the operation to every channel. That means if there is an image with three channel, with 3 channel, so you will be performing an operation of a kernel with a channel. Okay, so one with red. Okay, just perform kernel. One with green, perform. And one with blue, perform. All right, so channel wise you have to perform the operation of kernel. I will be showing more on it. And then it has been also told you have to perform point wise operation. For point wise you are taking 1 cross 1 matrix to further reduce the size. Okay, that means you want to reduce the number of operations. Reduce the number of operations. Okay, so that's the idea. If you want to build some architecture from your side, how you can reduce the number of operations from your side, because it's not only the deal that you are going to increase the accuracy. No, I already told in the previous class also, you have to reduce the number of operation, how many multiplications, how many addition, how many subtraction has been done. Because by doing this performance your computer will work, computations will be done. We want to reduce the number of computations and we want to increase the accuracy of detection. That's the research, that's the novelty, you have to bring that. Okay, so let me share my entire screen now and let's talk about the drawback of inception and exception, how it did a better, it gave a better results. Okay, so here it is. In limitations of inception, complex in nature, training time, fine tuning difficulty. See, inception v3 was having 42 layers. Okay, so now we were working on more layers. Okay, with 16 and 19 we were having that much numbers of convolution, but in case of v3 we are working with 42 layers. So that's good number. And the organization of these layers are like, the size of the image should not diminish. Okay, with smaller data set it's going to overfit. Model size is quite large. It is less suitable for deployment on devices. For example, small devices, if you want to use the classification, okay, so in that particular cases, V3 is not suggested. Okay, it is not suitable for all types of tasks. Like it is designed for image classification, object detection. We can do that. It may not perform well for segmentation, for generative modeling also. It requires pre-processing. Inception requires significant pre-processing, normalization, resizing. Okay, and the size of the image also, which we give here as an input, is 299. That is a large size. We were working with 224 in case of VGG 16 and 19. Here we want 299. So size will be more. High memory consumption. Okay, limited flexibility. So we are having some issues with V3. However, V3 is not like it's a poor algorithm by just notifying the limitations. No, not at all. V3 still remains highly efficient and powerful model. We have seen, in fact, in my all the projects I have used Inception v3 with attention. Okay, just add V3 with attention mechanism. You are going to get 90% plus score in classification. I got it. Fine. Anyways, by seeing these issues, in concern with these issues, we proceeded ahead for another algorithm, that is exception algorithm. Okay, fine. So exception algorithm do perform depth-wise separable convolution. Okay, in depth-wise, we split the convolution operation into two steps. Okay, how? As I told, a 2D filter is applied to input channels separately. If you are having three channel R, G, B, so apply filter separately to these channels. So if the input is having C channel, you will apply K cross K kernel to this C channel. Pointwise means you are having one cross one convolution. That is also applied to all the channels to combine the output of the depthwise convolution. So this is what you have to do, and this is what you have to do. In two step, this depthwise separable convolution has been divided. Okay, fine. This is your inception. It's a parallel arrangement of convolution layers. Okay, the blocks. Fine. This is what you have used in inception V3. We have already studied. But exception is more aggressive. It enhances the inception model. Okay. So you can see here, for example, I am having an image of a leaf. Here, pointwise convolution has been done, and then depthwise convolution has been done, and then all are like merged. Okay, so you are having an image, you are having pointwise convolution, you are going to get the result, and then here depthwise convolution has been done. What will be the depth of that particular image? That much filters will be applied. Okay, to a convolution. Okay, we'll be seeing more mass related to it. This is the architecture of exception. You are having entry flow, middle flow, and exit flow. That's what you are having in exception. Okay, so let's talk more about this thing, how this architecture is working. Depthwise convolution, a single filter is applied to each input channel separately. So if you are having a filter K cross K, let's apply this filter to red also, to green also, to blue also, separately. For example, if an image is having three color, that's what I have given you the description. Okay. Then pointwise convolution. After depthwise convolution, a pointwise convolution is applied. That means one cross one filter combine the output of the depthwise convolution into a single frame. Okay, that means here a chest X-ray image has been taken, and here n cross n convolution. That's a general process, I guess. Okay, or I would say here n cross n convolution applied. Then this is what the channel I'm getting. Then one cross one is applied. Okay, and then in another case, that's a standard CNN first one. This is standard CNN. This is how we work in convolution neural network. It's in general case, the first diagram. We apply convolution, feature extraction, then pooling. So after performing the feature extraction with number of kernels, you will get this much depth. Okay, then they are applying one cross one to get this result. However, in second case, this is depthwise separable. So first, if this is RGB, so R, G, B, these are separated. These are separated. and after separation, a kernel has been applied on all these three channels. Whatever be the result you are going to get. Okay, here it has been now concatenated, and then 1 cross 1 is applied to get the final answer. Okay, so exception utilizes a modified version of this which we have seen above. Yesterday also I told that in the original depthwise separable, we first perform depthwise convolution and then pointwise convolution. I think that's what we are doing, depthwise and pointwise. Okay, so this is depthwise because we are taking three separately, and this is pointwise. Okay, the exception performs pointwise and then the depthwise. Okay, there is a change. The exception perform pointwise first and then depthwise. What we have seen above is depthwise first and then pointwise operation. So exception do the reverse of that. And it is having three parts in the architecture as we have seen above. Entry flow, middle flow, and the exit flow. Three flows it is having. So in the entry flow, this is you give the input image 299, 299, 3. That is the expectation of your exception architecture. Just like inception v3, it also accept this size of image. Then this image will pass through 3 cross 3 convolution using 32 filter and 2 cross 2 striding. This will reduce the image obviously. This is feature extraction. And for non-linearity, we use ReLU activation function. Then again 3 cross 3 convolution with 64 filter and ReLU is used. After the initial low level feature extraction, the modified depthwise separable convolution is applied. So initially you perform a normal convolution as you do. Okay, fine. You are having an image, you give it to convolution. Okay, convolution. Okay, that's what you have to give. Then after that, you have to perform depthwise. Okay, what they are saying related to it? They are saying that, okay, here you have to, okay, so yeah, here. After the initial low level feature extraction, whatever you extracted, fine. The modified depthwise convolution layer is applied along with 1 cross 1 convolution. Okay, so here you can see in the given architecture. This is initial convolution 3 cross 3, 32, 64. This is low level. Done. After these two, then I am going to apply the depthwise. Separable convolution, separable. This is depthwise. Separable convolution, separable. Separable means separate the channels. How many number of channels you are going to get here? I guess after this now I am going to get 64 channel, because here I am having 64 kernels. So as many as number of kernels now you are having, you will get that much number of channel. So here you are having 64. Okay, and now you are performing separable convolution with it. So you're going to separate all. Okay, here it's 128, 128, striding 2 by 2. So 2 by 2, all these things now are having some relation. Then pooling. Okay, so separable convolution, separable, then pooling layer. Okay, and you are also attaching one convolution here that you are going to apply at this particular end. Okay, so separate and then apply this 1 cross 1 also. Again, separable, separable, then pooling. Okay, then again attach convolution here. Then separable, separable, then pooling, then attach convolution here. That is entry, and that's what they have explained here. Okay, so the initial, after initial, you are going to apply separable convolution layer with 1 cross 1 convolution and max pooling with striding 2 that reduce the feature map. So your image will be reduced here. After that, after that, there is a middle flow. One more block we are having. This block is repeated 8 times Each repetition consists of depthwise separable convolution with 728 filter and 3. Again, see, this all game is about CNN. Okay, this is again separable, separable, separable. I am having three separable convolution. I will be showing you separable more ahead. Okay, so I'm having three separable, which is repeated 8 times. So one time this block, this three all one time, then again, then again, then again, then again, 6, 7, 8 times. This is middle flow. Okay, and then after that, exit flow. We'll move to the exit flow. What happens in the exit flow? See, exit flow. The separable convolution again is used with 728, 1024, 1536, and 208 filters. Now the filter size are been changed, all with 3 cross 3 kernel. Global average pooling has been used, and finally you are going to get the results. Okay, with logistic regression if it has been required for the classification task. Okay, that's what you have to do. Here is a logistic regression for classification. Okay, so 728, 1024, then 1536, 2048. These are the number of filters used in separable convolution. Then global average pooling to summarize everything. That means to average your values. Okay, I have already discussed about this layer. Then fully connected, that means the neural network. And at the last, logistic regression to classify the image. This is your exception architecture. Now, sir, can you please elaborate more about this separable convolution, because that's something which we want to know. Because in the entire exception, you have used this separable convolution only. Huh, we understood that, sir, you are separating the channel. We got it. Okay, and you are applying kernel to every channel. That's what you are doing. We got it. Anyways, this is a technique used in convolution to improve computational efficiency. And we are going to break the convolution operation into smaller operations, small and simple operation. Okay, there are two separable convolutions. One is the depthwise separable. Okay, that's what I already told, dividing the channels and applying the kernel to each channel, and pointwise. That means you have to take one cross one convolution across all channels. Just take one cross one across all the channels. Okay, so what is the advantage of doing this thing? How the complexity has been reduced? See, the formula for depthwise is the standard convolution for an input tensor is of size HWC, that is the image, height, width, and the channel. The number of operations are HWC and K square into C out, where C in and C out are the number of input and the output channels. K is the kernel. However, in depthwise, for each channel, we are doing this thing. For each channel, we are doing this operation. Height of the image, width of the image, channel, input channel, multiply by K square. That is K cross K. For each channel, we are doing this thing only. Then we are performing pointwise across all the channel. That means pointwise is just one cross one now. So that is pointwise multiplication only. You are having HWC, H cross W, this is the width, and these are the number of channels. Okay, fine. And you are going to apply one cross one to each channel. This is one cross one. Okay, the one cross means only one element. There is one element here in the matrix. You are going to multiply with every channel. Okay, that's what you have to do. So multiplication. If you want to combine these two operations, how exception do? So combined operation is HWC input into K square for depthwise and C out for your pointwise. So just take this thing common, and this is what I'm going to left with. Okay, now sir, can you please tell us some numerical, some values, so that will be more understood. Okay, see here. This is the height of the image. This is the width of the image. Let us say 299, 299. You are having three channel RGB. Let us suppose the kernel size is 3. So it will be 3 cross 3 kernel. Okay. Let us suppose the input number of channels, output number of channels are 64. 64 are the output channels. Okay, so what you are going to do? See, you are having R, G, B, three channel. That's what you are having. Okay, fine. And then, yeah, we can increase the efficiency of the work with grayscale. Yes, we can do that by modifying the input layer, replace the input layer by except HW1. Yes, sir, we can do that. In grayscale, now we are having only one channel. But sir, now we are using these pre-trained models. So these pre-trained models are trained over three color. Okay, so in that particular case, now I'm just following this RGB only. That's the reason. With grayscale, we are having only one. Okay. So R, G, B, three channel. Now you are having a kernel, okay, whose size is D cross D. Apply D cross D to each channel. Okay, apply D cross D to each channel. You will be having a matrix for this green, you will be having a matrix for this blue, you will be having a matrix for this red. That's what you will be having. Okay, because you are presenting image in three channel, your image is represented in three channel, so you will be having matrix of image for these three channels. However, if you are having a grayscale image, so grayscale image, same information is projected in these three channels. That's something you know, I already told. Now you have to apply filter separately. That's what you have to do. Okay, apply the filter separately. Okay, so what will happen? What will happen? In standard convolution, this is the image shape, width, height, and RGB. This is k square, that is the kernel, 3 cross 3, and this is 64, for example, the number of channels. Okay, so this much operations are required in standard convolution. But what will happen here with our case? In our case, in depth wise, this will happen 224 into 3 square. Okay, into 3 square. This much number of operations will be done. And after that, you are going to perform pointwise operation. In pointwise, this is your image, width, height, and channel, that means RGB, and output is 64. Output is 64. Okay, so multiply with 64. That's it. So it will give you another, the number of whatever be the number is, you are going to get it. And if you total, these are the total number of operations which you need to perform. So in general case, you perform this much operations. With exception, you have to perform this much operation. Okay, in total, this much. So if you can divide these two, I think you will be in a good state where the number of proportions are reduced. The number of operations are reduced. Okay, fine. All right. So this is the operation which we do depth-wise. Okay, again check the diagram. Again check the diagram. Here it is. You are having an image, and we are having an exception. They told we first perform pointwise. This is the matrix which you are going to get. Then you are separating it according to the channel. Here you are performing depthwise operation. You are going to get this result. Then merge. You are having separable convolutions, and depthwise, pointwise are separable convolution. Just split the image, perform the operation, combine. Okay, got it. So yeah, here now it's mentioned exception model is been used in many of the use cases application, like plant disease detection, also malware detection. Okay, we can use it like many of the use cases. Okay, leaf disease detection, plant disease. Okay, chest X-ray also it has been used. I have also used this architecture. Okay, this exception one. Okay, and if we just check out the code for it, just check the code for this exception. Separable convolution also I will show you. Okay, so this is the code for exception. We are having entry flow. In entry, we will start with 32 convolution, then 64 convolution. Verify that is only mentioned in the architecture. Let me show you. Let us verify this architecture. See, if you check the diagram, 32, 64. Two convolution layers. Okay, in between, they are batch normalization and other things also to prevent the overfitting in the model. After that, you are having three residual blocks which are of separable convolution. See, here also we are having three residual blocks. This is one residual block, this is another residual block, this is another residual block. Three residual block for separable convolution. That's what we are having. Okay, fine. Yes, there is no images are less in the data set model is convenient. So number of images is less than the model is overfitting, sir. Whether you are going to use any of the model with less number, it's overfitted. Okay, so these are three residual connections. So how we can make this three residual connection? Now here it is. You are going to take here you are going to take in the first block 128, in the second block 256, and the third block 728 number of filters. Again, separable convolution is again a convolution only. इसको लेकर कोई टेंशन नहीं. Don't get tensed. This is again convolution only. See, so I am having separable convolution number of filter 128, then number of filter 256. Okay, that's what I'm having. And yeah, I think here it can take 128, then okay, 3 now it's 3. So with 3 I'm having 1 cross 1 striding to batch normalization. This is a residual connection. This is residual connection. So first you will make 128 128 this block, then make 256 256, then make 728 728. See the architecture. That's what mentioned. 128 128, then 256 256, then 728 728. This is how architecture has been built here. Okay, in coding also it's clearly mentioned. So just keep one residual connection of 1 cross 1 1. Okay, this is 1 1 of size. All right, rest is your separable convolution. Okay, and what's happening in separable convolution? Depth wise and point wise. That is what happening. Separable. As many as channels are coming, separate. Perform point wise on it. Perform depth wise on it. Add. Okay, add. Add x plus residual, x comma residual, and return. This is entry flow. In middle flow, you are having loop for I in range of 8, and you are having this separable convolution, separable convolution, separable convolution, 728, 728, 728, 8 blocks are there. And then you are having exit flow, 728, 1024. Okay, like this. This is residual connection, 728, 1024, then pooling, then 1536, then 2048. This is how separable convolution are there. That's it. Now you can build your exception. Now you might be thinking how the scientists, how the researchers can think that we have to organize the layers in this way. See, they have focused upon the problem. They have focused upon the problem. What is the problem? Problem is related to, in research, again, I am just repeating the same thing, related to complexity and related to scores, accuracy. Now, are we able to make such kind of architectures? That is a question. That is the question. In an image, if you want to use convolution, the basic operation you should be knowing. We are having an image, we do convert it into matrix, we apply kernel. We got another matrix that is called as a feature map. That's what we have learned. As the number of filters increase, the channels increase. And if we use standard convolution only, that means if you are having image with this much number of channels, that means this much depth if you are having, okay, you will be having dot 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 up to this much depth you are having, okay, this much number of channels. And if you apply what, because next in your feature map you will be having this much channel, and again you have to apply the convolution. Again, after feature map you are getting na image, this is the matrix, you apply kernel, you got the feature map, then you perform the pooling. After pooling, again you are going to get a result, then again you are going to apply convolution here, again you are having a filter. What is the size got increased, so your image size is getting less, channels are getting increased. If you start with convolution 32, so 32 channel will be there. Then you add another convolution with 64 channel, 64 filter, so again it is increased to 64, size of the image will be reduced. So in vgg 16, 19 and all these, you started with an image of 224 cross 224 width and the height, or 299 299 with the width and height, you got reduced it to 77. This is the size which you got of an image after applying this vgg 19 and all these stuff. ओके, इतना छोटा साइज हो गया इमेज का, वेरी लेस साइज. अच्छा, चैनल्स कितने बढ़ गए सर? 1048 सर. इतनी डेप्थ बढ़ गई है, डेप्थ. दिस इज द डेप्थ इंक्रीज्ड. अब द साइंटिस्ट दे थॉट वी नीड टू रिड्यूस द ओके, फैक्टराइजेशन तो आपने इंसेप्शन में यू ऑलरेडी टोल्ड. नाउ द नेक्स्ट थिंग इज we need to reduce the computation, number of computations, because in a standard format what you are doing is you are going to get the result from hw, height, width, number of channel into number of filters. That means number of filters, that means size of the filter. As this, and see out, this is out, see out. That means if you are having rgb image, this is what you are going to input, then this filter is applied over this image, this much number of channels will be added to an image. So like this much computation needs to be done. Then Depthwise came and it told that okay, no, hw, if this is three channel, so just only we are having d cross d only, every channel, every single channel, this operation. Okay, so it's better if you are having three channel, your image will be splitted into the different channels R, G, B. Three channels it will be splitted. You will perform separately. D cross D to here, then D cross D to here, then D cross D to here. Apply separately. Not take it as a whole. whole, complete. No, just separate it and apply operation. So there will be one operation here for a channel. एंड इफ यू से सर दिस इज वन दिस इज टू, ओके ऐड ना, चलो ठीक है, तुमको लग रहा है सर ये एक ऑपरेशन हुआ, ये एक ऑपरेशन, ये ऑपरेशन हुआ, तो सर आप बोल रहे हो यू आर हैविंग ओनली वन ऑपरेशन, चलो ऐड भी कर दो तो यार 3 टाइम्स हो जाएगा, 3 into this, तो वो तो स्क्वायर से तो कम ही है ना भाई। ठीक है, इस बात को इग्नोर किया गया अभी। जस्ट सेपरेट द चैनल, मल्टीप्लाई विद द कर्नल, दैट्स इट, ये करा। और फिर पॉइंट वाइज में 1 क्रॉस 1 है, वो सिंगल पॉइंट टू पॉइंट मल्टीप्लीकेशन है, दैट इज पॉइंट वाइज। ओके, क्योंकि वाई इफ यू डू द पॉइंट वाइज ऑपरेशन, तो क्या क्या हो जाएगा, इफ यू आर हैविंग जस्ट ऐसा है 1 2 3 4, एंड इफ यू आर हैविंग दिस वन, ओनली वन वन एलिमेंट, तो वन को वन से मल्टीप्लाई। ओके, दिस इज व्हाट हैपन्स। तो आपकी ये जो मैट्रिक्स है ना, सबसे जो मल्टीप्लाई होगा, सो लाइक वन, देन आई गेस प्लस ऐसे करते हुए टू, 1 into 2 इज 2, देन 1 into 3 इज 3, एंड देन 1 into 4 इज 4। ये कहीं ना कहीं इट्स रिड्यूसिंग द ऑपरेशन 1 क्रॉस 1। तो ऑपरेशंस का खेल है यहाँ पर एक्सेप्शन में, कैसे कम कर दिया। That is up, if you come across separable convolution, separable means depth-wise and point-wise, that is separable convolution। ये channel split करो and this is 1 क्रॉस 1, combine करो, that is exception। Okay, fine, so this is the code, I have also referred to the code, all right, and yes, I have used so many projects in this regards only, I made so many projects, for example, this is breast cancer project. Okay, so I have used VGG16, same architecture I have explained in previous classes, also using multi-head attention. Okay, data, if you want to see the data, okay, let me show you the visualization. 5 images, yeah, here it is. This is breast cancer images, X-ray images. Okay, we can convert it into standard format, RGB 224. We can apply VGG16, VGG19, inception V3, exception. We can apply all. Okay, here you can see. So, like exception, here is the exception algorithm. Same, I just changed the name. Just copy the code of VGG16, paste it down. Instead of 16, just use exception. Everything is same. Okay, I'm just using these layers also. Gaussian noise, global average, batch, everything is same. And the good thing is, if you say, sir, we want to make our own architecture, see, that will be a bit complicated process. I'm not denying you can make your own CNN pooling, CNN pooling, you can parallelize, you can asymmetry, you can bring depth wise convolution, you can do everything. I'm not denying that fact. You can do, you can add attention mechanism also, you can do. But you know what we are getting here with the pre-trained model, why I'm suggesting you the pre-trained model, we are getting the trained weights already. So these models which are pre-trained models, we are getting the weights. That means we do not have to start from scratch. Okay, that means if adding a layer, then performing pooling, adding layer, performing pooling, this is scratch. That means now you are building something which we want to make a architecture to know, to get aware that this is zero. With pre-trained models, I don't want to start with zero. No, I want to start with some knowledge. Now next, there are many research papers came where they have used their own techniques, so you can take those architectures, those weights, and then apply techniques, apply rest of the layers. And that's what I did now. You might be working in different problems, like just I have shown na, this is breast cancer. भाई ये ब्रेस्ट कैंसर का डेटा है, मैं यही अल्गोरिदम सेम अल्गोरिदम मैं अभी ब्रेन ट्यूमर पे लगा दूंगा। और ऐसा नहीं है, इफ आई डू अप्लाई दिस अल्गोरिदम ब्रेन ट्यूमर डजंट मीन दैट आई विल फेल ना, आई विल अगेन पास। I can apply this algorithm to Parkinson disease. I can apply this algorithm to autism detection. Not I can apply, I did applied. Okay, this is breast cancer. Na? What result you got from exception? See, exception, 89% accuracy. Okay, you are getting 89% accuracy with exception using multi-head attention. Okay, how many iterations are did? Only 5 iterations are did with 89% accuracy. Okay, you can follow up with some more change. You can enhance this algorithm just by adding few more, like, okay, decrease some number of dense neurons. Okay, here I added batch normalization. You can avoid Gaussian noise. If you think that, sir, what can be done if I can avoid the Gaussian noise, you can avoid the Gaussian noise also, you can do that. Yes sir, Sohail sir, do you have any question, please? Okay, I got this raised hand now. Okay, fine. So you can do from your side. This is breast cancer project. This much accuracy. I'm getting fine result with that. Okay. And this is satellite classification. Now I'm going, let me take another data set apart from the medical imaging. This is satellite images. Okay, and if I want to work on satellite images, let's see. Satellite images are not the medical images, they are not at all medical. But see the approach. ये देखो, ये क्या है, ये कौन सा आर्किटेक्चर है, ये कौन सा, विच आर्किटेक्चर आई एम शोइंग यू, आई हैव यूज्ड दिस आर्किटेक्चर ऑन मेडिकल इमेजिंग, सेम ऑन 5 इटरेशन सी। और ये कोई छोटा मोटा क्लासिफिकेशन नहीं था। हियर आई एम हैविंग 0 to 14 classes, not only 1 class, 2 class, 3 class, 14 classes। 0 to 13 मीन्स ये तो मल्टी क्लास और ज्यादा क्लासेस को डिवाइड कर दिया। सी द एक्यूरेसी, भाई इतनी क्लासेस पे इतनी एक्यूरेसी VGG 16 ने दी है। 70% VGG 16 gave the accuracy. Okay, let's use VGG 19, same architecture using multi-head attention, accuracy। okay, यहाँ पर ये डिप हो गया। okay, डिप हो गया। आई थिंक देयर माइट बी सम इशू, मुझे लग रहा है इशू कैन बी, नहीं ठीक है। ओके चलो, and then I proceeded ahead with inception. Inception, see what it is doing. Inception 57, तो 14 classes पर, if you want to do something, 14 classes का classification, it's never been easy। 57 inception। now see what the exception is doing। exception same architecture, ये देखो 78। so VGG was like 70, exception is 78% accuracy। and here I'm getting balanced precision recall also, not that much issue, but I'm getting good scores। फिर भी ठीक है। तो सैटेलाइट इमेजेस इफ यू वांट टू सी, तो और ये अलग ही थी सैटेलाइट इमेजेस। okay, let me show you the images what I am having। हाँ, here it is, these are satellite images। अब इसमें से if I am getting 78% accuracy also with 14 classes with a pre-trained model using attention, अभी तक के लिए तो ठीक है। these are the classes which are available with me, you can see। and these are tiny images, satellite की images हैं ये, direct वाली नहीं है। they are satellite, so these are already tiny images। how I can identify that which is a land, which is a mountain, which is a road, how I can identify। बट मेरा मॉडल वो एक्सेप्शन वाला 78% एक्यूरेसी पर चला गया with multi-head attention using Gaussian noise also। this is satellite, this is blood cancer। blood cancer में In case of blood cancer, okay, what I am having, let me show you. In case of blood cancer, huh, I am having again, I think, four category. This is blood cancer: benign, malignant, and malignant is a type of, matlab, means hard cancer. That means, so malignant, pre-B, pro-B, and early pre-B. Three classes I'm having, and this is benign. Now you are seeing that, sir, ये तो images एक जैसी तो दिख रहा, same, they are looking all same, color. These are cells, blood cancer like cells images, blood cells images. Okay, so let's see again. Check my code. You know the flow. पूरा flow same है. Okay, and here I used Inception V3. Okay, 97% with Inception V3 multi-head attention. That's why I'm saying, okay, if you're trying to build something from scratch, na, that is something hectic. You just take the trained weights of an image, na, then do something over that particular. Add few more layers. Change the activation function if it is possible. Get some research papers to be done and see what problem statement they are facing. And then what else you can do? You have to learn some maths. Okay, you have to learn some maths. And these all architectures are being tested, verified over the benchmark data set. तो मुझे कोई इतना issue नहीं है. Okay, 97% with Inception, and with exception, with multi-head, I am getting 98%. Okay, again 97, 98% accuracy for detection. I can show ovarian cancer also. And you can see my all architectures are same. I am having different projects, different images: chest x-ray, brain tumor, ovarian cancer, blood cancer, satellite images, but the architecture which I'm using is same. See, this is ovarian cancer. Okay, and you can see the results. How ovarian cancer images looks like. Let's see how it looks. Here it is. Okay, so here it is. One, two, three, four, five classes. Five classes I am having, and okay, the number of images are 1,000 plus for each and every category. Okay, and I expecting you should be working on minimum 10,000. You should work on minimum 10,000 per category. I will be showing some augmentation also. Today, I will be showing some augmented images also, like rotation, flip, that also I have included. Anyways, so this is ovarian images, and differential attention I've already shown you previously, I guess. And apart from that, with differential attention, these are the scores I'm getting: 70% accuracy. With non-differential also you can make, and I'm damn sure that without differential, we using multi-head, you can increase this score to 80 to 90. Definitely you can increase this score to 90%. Ovarian cancer. Okay, 75% with exception. With mobile net, today I will talk about mobile net architecture also. With mobile net I got 81%. Mobile net is a small architecture. Okay, that's for devices, small devices. For example, on mobile we can run this algorithm to perform the classification. Mobile net. Inception is heavy, exception is small, mobile net is more small. Okay, so it's proved to be better. Mobile net. Autism, yesterday only I have shown you. In autism also same thing I have applied. Okay, in chest x-ray, you very well know, same thing I have applied. Chest x-ray classification also. Yesterday I have been told that, sir, Parkinson disease detection, can you show the Parkinson also? Yes, please check the Parkinson. Okay, this is Parkinson. All right. So, how the data looks like for Parkinson? This is the images, like handwritten. ये medical की भी नहीं है. ये तो these images, a person who is having a problem of Parkinson. Okay, if you give a pencil to that person, and and you can ask that person to draw. Because of lack of concentration, a person who is having Parkinson problem, na, that will draw the images like this. A healthy person is concentrated. Parkinson person is not concentrated. Such kind of images. So yeah, in these images also, again the same flow, inception v3, same code, inception v3 for classification. You can see 100% accuracy. Anyways, I'm just skipping this. 100% accuracy is not something which we do expect, but the data set is less on that inception exception. Everyone is like 100% only. Okay, exception is 88% here. So that can be overfitted over small images, but exception is not overfitted. It is giving 88% accuracy. So inception is overfitted on small data. 100% is overfitting, but exception gave 88% accuracy. That means it is not overfitted. We need to increase the data. That's why I told you should have a good number of images. For each category, at least you should have 10,000. Okay, so if you are having a 30,000 data, in case if you don't have, then obviously you need to perform the augmentation. So how you need to perform the augmentation? Okay, let me tell you, because I'm having one more. This is fetal ultrasound. Okay, so in fetal ultrasound, I am having images like this. Again, this is the images of fetal. Okay, three classes I am having. Okay, and then I applied my own technique. The data set is less because such kind of data is like, okay, it's not available. I collected this data set from one research paper. Their link was mentioned of some hospital data. Now, this architecture, which I created by my own, and it doesn't have any pre-trained model. See what I did? Very small architecture. CNN pooling, CNN pooling, CNN pooling flatten. So only three convolution with pooling: 32 filter, 64 filter, 128 filter, then flat. Then I applied fully connected like dense layer 128 and 3, because it's a multi classification. I trained this architecture only, just this architecture only I trained 93% accuracy. This will be further reduced if the data would be more. So you go ahead with small architectures first. If you are being a research person, at least you should demonstrate how CNN pooling works. You have to, if the model is overfitting, then include batch normalization also here. Then slightly increase Gaussian noise also here. Go step by step. Then try to, sir, can we add more convolution? Then it's you should try to make parallel connections. Perform factorization. Include a skip connection. Include attention mechanism. Try to get something out of it. Try from your side. That is something, if you want to build your own architecture which you think that okay, this is what something which I am giving as a novel architecture from my side. Apart from that, use pre-train, and then add some maths, some layers, some techniques, okay, which will enhance the capability of that pre-trained architecture. So this is inception v3, and I use this architecture, and in inception v3 I got 79% accuracy. With simple architecture I got 93. With inception I'm getting 79. Okay, here the model is a bit struggling, but 79 okay. But I am not saying that it's okay and it's not overfitted. 79 is not an overfitted model. Not overfitted or what? How's the training? In training we got 95, so it's showing overfitting. Yes, training accuracy is 95. Testing accuracy is 79. Model is showing overfitting. That means it is struggling to understand the data. And why? Because of less number of pictures. So the point got validated. Okay, here then exception, same architecture, 82%. What is the training accuracy with exception? it is 95 again. So just थोड़ा सा overfitting improve करा. Okay, we reached to 82. 95 training, 82 testing. Overfitting तो है, still overfitting is there, but improve करा अपन from inception. Okay, then okay, exception with attention. Previous architectures were without attention. Now this is exception with attention. What is the score? Accuracy 94, training, testing 74. Okay, so attention didn't improve. Okay, and with inception and attention, the score is like 36. We further fail. That means model is struggling to classify. Actually, this data was not given to me as a classified data. Different folders, they are not kept. This data, I was having only one folder and all the images are present in that folder only. What I did, if I show you, in case if you are having a data which is not given as in form of class, so I created clusters. Let me show you what I did. You know, I was having data. Huh. I was having data like this. Okay. All the images are in one folder only. This kind of data I was having. Then what I did is I applied VGG16 and I extracted features from the images. Then I applied K-means clustering to create separate cluster from these features. That's what I did. You can apply VGG16, you can apply any other algorithm to extract the feature from the images. Okay, like DenseNet or whatever you want to apply. DenseNet is proved to be better. Okay, so that's also you can do. Okay, got it. So I applied this thing, then I performed K-means clustering, then I created data frame. Okay, and then I performed the classification. Okay, so such kind of data was, in fact, I was trying to post the project over LinkedIn also, but LinkedIn was rejecting. वो पोस्ट नहीं होने दे रहा था क्योंकि टाइटल एंड दिस इज ना देख सकते हैं fetal ultrasound. These images were there, but I got the data of some not of India. This data set of some outside country were related to the hospital data set, and I accessed the data, I downloaded, then I performed clustering, then I applied my techniques over it, algorithms to perform the classification. Okay, then I am having one more project which I did. This is your project related to melanoma cancer, skin cancer. Okay, and in skin cancer also, like I applied the same techniques. No, no, no. I could apply the same techniques. Here it is. I applied exception algorithm on melanoma. I got the result. This is simple exception. I got 89% accuracy without attention. Without attention. This is simple exception algorithm. So you will not be having novelty if you apply pre-trained architecture with the already already available, like which you do in general case. You have to create either your own layer. That's what you have to do. So that layer, that mechanism should be added with this. That will bring the novelty. What that layer could be? See, I am already introducing this attention mechanism, and attention. I already told you that after performing this entire stuff, then add attention. Don't add attention in the intermediate, as the complexity will get increased. You are using multi-head. How many heads you are using? I use 8 heads. You can increase the number of hits. See, that's what you have to think. According to the number of images, if the number of images is more, data set is more, increase the number of head. 16 head, 32 head. You can do that. Okay, fine. So this is a simple like architecture of exception. Now, bone fracture. In bone fracture, I did one request which has been given to me that, sir, kindly apply the augmentation here in the bone fracture. I did in any project how we are going to do. So in bone fracture, I did apply the augmentation. Okay, let me refresh this and show you. In my existing code only, you can add the augmentation. For example, I am having images of bone fracture, X-ray images. Okay, and how they looks like? This is how they looks like. This is how the images looks. Okay, how many number of images I am having for the fracture? Non-fracture, how many number of images? I am having 4 fractured, 4383 non-fractured, not fractured, and this is validation image. They are also, that means 4,000 plus images I am having here in training. Then what I did? See, ये कोड वही है, सेम कोड है. This code is all same which I use in each and every project. Everything is same. I made a data frame. You very well know. I always make a data frame. You have to also make a data frame. Okay. Then after making data frame, I perform oversampling to equalize the image. 4480, I made it equal. After that, after that, after that, what I did is I perform I perform splitting of the data. That means training, testing, and validation. I perform splitting, training, testing, and validation. Then here, in case of training the data, in training the data, here, just check this code. In training the data, during pre-processing, I performed rotation, width shift, height shift, shear, zoom, horizontal flip, all these things I did. This is what you call as augmentation. I applied all these transformations over the image. There are many ways you can perform. Either you can see, there are many ways you can perform. For example, you are having, for example, now listen to me carefully. For example, you are having 100 images. You are having 100 images. You can apply a rotation of any angle, let us suppose 45-degree, to each image, and you can keep these 100 image, and you can keep those 45 rotated images also in the same folder, so now it will become 200 images. Got it? Then on this 200 images, you can perform horizontal flip. So on every 200, okay, existing 200 will remain, plus 200 flipped images will also become. Now this will become 400. But what I have used, these operations are not one by one. These are all together on an image. I scaled the image, I rotated by 40, then I performed the shifting, height shift, width shift, shear, all the thing I did. I did. Okay, so I am having 7,000 plus training, then 800, these are validation. So in previously also, if you count another number of images, count these. Okay, 4, and 4, count. This is 8,000 something. Same here, 8,000 something, which I'm getting. But augmented images, like I'm having rotated, flipped, and all these things I'm having in this here. So this one portion of code I added. Rest is all same. Binary, class mode, RGB color, same. Everything is same. Yesterday I have been asked that, sir, can you perform this kind of augmentation where you can perform, because oversampling, sir, you have already told. Can you perform this such kind of operations also? Yes, I can perform such kind of operation. Okay, I did this thing. Then just use the model. I use VGG16 with attention head, multi attention, same. multi-head attention VGG16, and 99%. With VGG16, 99% accuracy. And you see the images I rotated also, flipped also, this also, that also, I did perform everything with the images, X-ray images. And these are not 4,000, at least 7,000 images are present in the training. I trained with 7,000. This is what I get. Apart from that, you can do, okay, sampling I did to increase the number. So you can do that code also I have shown yesterday, that if you are having x comma y, that means these are the images. These like this is okay, just these are the images. Okay, so you can split it into training, testing, and validation. With training you can perform sampling, you can sample training, okay, and make all equal. Then you can perform augmentation, like what I did just recently. That's what you can do. Then train your model over this. Then perform testing. Then validate also. During training, validate also with this data. Later on, you can perform testing. This code was also available to you yesterday. I have shown in Spine 1, Spine X ray. This code I have already shown. And I have made all the codes to you today. In morning itself, I have made. Okay, fine. So this is with the bone fracture. And if I don't use VGG16 multi-head, if I use simple architecture, for example, this is simple architecture. Okay, in simple architecture, I am getting the score as 50%. Struggling. Model struggled. Simple architecture, it struggled. Then I increase the architectures like, okay, convolution pooling, increase the architecture. Okay, then 49%, still struggling. Then efficient net, another pre-trained model, efficient net. This I used, and after using efficient net, struggle. इसका तो रिजल्ट भी प्रिंट नहीं करा मैंने. Efficient net I used, but I haven't printed the result of efficient net because during training only I have seen 51% accuracy, so it's failed. Then I use exception. यहाँ पर कोई मल्टी हेड यूज नहीं करा, नो मल्टी हेड, जस्ट एक्सेप्शन. The result with exception is 99%. So at exception without attention head, it success, it got success. तो मल्टी हेड से क्या होगा, फिर मल्टी हेड से भी चेक कर लेंगे. You can use this thing with multi head also. तो गॉशियन नॉइस एंड मल्टी हेड, इनका कॉम्बिनेशन बड़ा जबरदस्त है. ओके, देन आई यूज रेसनेट 50 रेसिडुअल, ये भी एक प्री ट्रेन आर्किटेक्चर है. ओके, सो रेसनेट 50 अगेन ओनली 50% एक्यूरेसी, फेल. मुझे जो सक्सेसफुल आर्किटेक्चर अभी तक मेरा जो रिसर्च सामने आया, द सक्सेसफुल आर्किटेक्चर्स विच आई गॉट इज, ओके, VGG 16, 19 और इंसेप्शन V3 और एक्सेप्शन विद मल्टी हेड अटेंशन विद गॉशियन नॉइस, ये सक्सेसफुल है. अभी तक तो मेरे को ये मिला, क्योंकि आई डिड ट्राइड विद मल्टी हेड विद अदर ऑल्सो, बट देयर आई वॉज नॉट सक्सेस. विद रेसनेट आई ट्राइड, रेसिडुअल नेट, सक्सेस नहीं मिला मुझे. एफिशिएंट नेट के साथ भी नहीं मिला सक्सेस, लेकिन इसके साथ मिल रहा है, इनके साथ. द काइंड ऑफ आर्किटेक्चर विच दे आर हैविंग ना, दिस इज सपोर्टेड, मल्टी हेड गॉशियन नॉइस, ओके, एंड गेटिंग गुड स्कोर्स. आपको भी मिलेगा, आप अपने डेटा पर 100 लगाओ, 100% यू विल गेट द रिजल्ट. ओके, आई एम हैविंग, बिकॉज लाइक आई बीन टोल्ड, तो सर और दूसरी अल्गोरिथम्स भी बताइएगा आप, जस्ट थोड़ा सा डिस्कशन कर लीजिएगा ऑन अदर अल्गोरिथम्स ऑल्सो. लेट अस सपोज मोबाइल नेट. सो मोबाइल नेट जो है, okay, we have seen 16, 19, inception, exception with all multi-head attention, Gaussian noise, all architecture, all project I have shown you. And there is just like a flow, same flow in each and every project. Approach is all same. make a data frame, draw some visualization, perform sampling, apply it to the model with multi-head. हाँ, मोबाइल नेट V2 भी अच्छा दे रहा था मुझे, आई फॉरगॉट. Mobile net is also good. Mobile net V2. This is also giving good score with multi-head and the Gaussian noise. Okay, what is present in mobile net? Mobile net is a small architecture. Okay, so mobile net is a lightweight CNN architecture. It is specially designed for mobile and embedded computer vision. That means if you want to perform classification and all the tasks, na, you can install this can be installed on mobile. Okay, REST architectures are huge architecture, heavy architecture. Mobile net is small architecture. Again, Google researchers developed it. Okay, so mobile nets. Remarkable aspect of this model is ability to strike a good balance between model size and accuracy. So, for example, this is an image 128, 128, then 64, 64, then 32, then 4. That means it is reducing, 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 then neural network. That's what we do. So, we are having 3 cross 3 convolution ReLU and 2 cross 2 max pooling. That's what we are having. So, how it's incorporated? MobileNet architecture incorporates several key features that contribute to its efficiency and effectiveness. And here we include depth-wise separable convolution. तो भाई ये आ गया exception, inverted residual, residual का उल्टा, invert the residuals, bottleneck design, linear bottleneck, squeeze and excitation blocks. So इतनी सारी चीजें हैं इसके अंदर, लेकिन आर्किटेक्चर इज स्मॉल. ओके, इतना सब कुछ है. Mobile net is used for image classification. Limited computational resources are required. It consists of series of convolution layers followed by depthwise separable convolution, inverted residual, bottleneck design. I will show. Depthwise separable convolution you very well know. अभी बताई दिया आज exception का फंडा. Inverted residual means inverted residual are the key component of mobile net that helps to improve the model accuracy. They introduce bottleneck structure that expands the number of channels before applying depthwise. So inverted residual increases the number of channels before applying to depthwise. The expansion allows the model to capture more complex features present in the data. So inverse residual increase the number of channel before applying to depthwise. Bottleneck reduces the computational cost by 1 cross 1 convolution to reduce the number of channels before applying to the depthwise, again 1 cross 1. Linear bottleneck introduced to address the issue of information loss. Instead of, it uses linear activation function instead of non-linear. In so far we were using ReLU. ReLU is non-linear activation function, but here it is saying that you have to use linear activation. What is linear activation? X, or I can say linear. This is linear activation function. Here they introduce squeeze and excitation block. It enhances the capability to perform recalibration. What is this skews and excitation? I have something to say about it. In SC block, the first is skews. It is a typical convolution. See, पूरा ही convolution है वो तो. Convolution के बिना तो कुछ है ही नहीं. Convolution, convolution, convolution. Everything is convolution. Everything is feature extraction. But the way the approach we are using convolution is, that's what we have to understand. So skews is also convolution. We have a feature map which contains activations like feature responses after applying filters. Each feature contains a lot of spatial information which may not all be relevant. The skews operation reduces the spatial information into single summary. We apply global average pooling to each channel. Apply global average pooling. So global average pooling you very well know. This layer, na, global average pooling, it calculate the average of all the values which are present in the matrix and give only one value. You have already seen this global average pooling. So skews is doing this thing only, global average pooling. It means for each channel in the feature map, compute the average value of the spatial position. Average कर लो पूरे का. Why it is important? Instead of keeping all the information, which might be too detailed and noisy, the skews helps to condense the essential information in each channel. तुम तो यार essential information है बस वो ले लो condense हो, बाकी हर एक की जरूरत नहीं. Not all. Just take the average. This is skews. What is excitation then? The skews vector, that is summary of all the channels, is passed through fully connected neural network. अब skews करने के बाद neural network है. The purpose of neural network is to model the dependencies between the channels and to learn the relation. That means the skews vector is passed through fully connected neural network, which reduces the dimensionality of the vector and helps in learning. Second layer restores the dimensionality back to the original. तो पहले dimension कम होंगे, then dimension will increase. So you are having two layers here. So first you have to perform the skews, and then you have to perform excitation. Excitation, reduce the dimension, reduce, then increase. Activation function, sigmoid activation function is used. Sigmoid is like between 0 to 1. It's a, it gives you probability. It gives the value between 0 to 1. That is sigmoid. So both the layers will be using sigmoid activation function. So skews is global average pooling. Excitation is neural network. Then activation function sigmoid is used. Two layers are used in excitation. Then recalibration. The final step is recalibration, where the original feature map is adjusted. That means scaling. We want to scale each channel to original feature map. So इन सब से पास करके वापस स्केल कर दो. That is amplification. Recalibration वापस से, because you are using mobile net. This is a small architect, small. It is only fetching relevant information. Mobile net, because it, we don't want this mobile net to work upon the entire data. Not every is important. Okay, not everything is important. And for feature extraction, we generally use CNN only. The entire this workshop is based upon CNN only. The question can be asked, sir, apart from CNN, if you don't want to CNN, then what are the techniques which we can use? Okay, you can use traditional machine learning algorithms to perform image classification. You can do that. Logistic regression, support vector machine, you do that to perform classification. Somewhere it also came into हाँ सर तो क्या कर सकते हैं हम क्या can we do this thing sir, can we can okay, there are many things which you can apply. सर एक काम करते हैं, we are having images, और सर we can extract features from these images. That's what we can do. करते हैं सर, feature extract कर लो इसके by applying any of the pre-trained model, either VGG16 or whatever, feature extract कर लो. उसको extract करने के बाद attention लगा दो. attention लगाने के बाद if it is possible machine learning technique लगा के classification करो. तो आप ये दिखाओ कि सर वी आर यूजिंग हाइब्रिड आर्किटेक्चर. सर आप अपने रिसर्च पेपर में हाइब्रिड आर्किटेक्चर दिखाओ. Deep learning also, attention mechanism also, machine learning also. Show that how much score you got here and what is the computational time. Hybrid बना लो, because there are many of the institutes which do ask the hybrid architecture. आप बताइए आपने रिसर्च में क्या लगाया, what is new in that. तो आप ऐसा कुछ you can try. ओके तो ये है. और नहीं CNN के अपार्ट फ्रॉम द CNN इज feature extraction major technique. If you don't want to use CNN, then directly use machine learning or deep learning, neural network. इससे तो कुछ खास नहीं होने वाला. CNN तो लगाना पड़ेगा. We have to use CNN और फिर इसको इनकॉर्पोरेट करो आप. ओके, गॉट इट. सो मोबाइल नेट भाई हमारे जो हैं, मोबाइल नेट ने पूरा सिंप्लीफिकेशन, ऑल सिंप्लीफिकेशन दे डू. They perform factorization also. They performed your the one done by exception, that is depth-wise also. Then they perform skews and excitation also. जितना छोटे से छोटा हो सकता सब कर दिया उन्होंने, स्मॉल. एंड देन रिकैलिब्रेशन, रिकैलिब्रेट कर दिया, यानी वापस से इंक्रीज कर दिया. ये लो. तो mobile net is also showing good scores to me. I've used this mobile net in some of the projects and I'm sure that it gave the good results. Okay, so adjust original feature map by scaling again back. Skews, excite, and recalibrate. Okay, so SE block, this skews and excitation introduces adaptive attention mechanism that helps the model to focus upon informative features and the channels. By recalibrating the feature maps, the network becomes more efficient. Okay, so applications are image classification, object detection, segmentation, medical image analysis. Skews and excitation is so much used. Not only this thing, we are having other techniques also, like DenseNet, densely connected convolution, this pre-trained models, which is having convolution designed to improve information gradient flow. It consists of dense blocks, which is having skip connection. Skip connection, what do you mean by skip connection? This is your architecture, and I am tapping it back here. This is skip connection. That means information should not have to be just reduced. Just again give it back here. Whatever here is here, give it back and add it to this. This is skip connection. So dense blocks, dense net, I'm having skip connection. I can reuse the feature. ये तो करा ना मैंने. Whatever be the feature present here, I am reusing here. So I will be not in a scarcity of feature. That is why dense net, dense block. So I can increase the number of blocks, increase the number of layers by reusing the feature value. This is dense net. This is skip connection. In ResNet, residual net, we are having skip connection. Okay, SkewsNet. SkewsNet is a lightweight CNN architecture to reduce the number of parameter and computational complexity. So it is having again skews and expand layer. So you have already seen the skews and excitation. Same approach is used here. This SkewsNet is called as a fire module. So what we have done in the skews, we have used global average pooling. So global average pooling will get the will find the average value of each and every channel. So here the skews layer is 1x1 convolution. होगा क्या? कम करना है ना आपको, size 1x1 कर दो, तो depth reduce कर देगा वो. 1x1 and expand the layer. A combination of 1x1 and 3x3 can increase the depth later on. So skews and excite. So 1x1 convolution reduces the number of channel. Before applying to the larger convolution, SkewsNet drastically reduces the number of parameter. तो ये चीज तो हमने इंसेप्शन में देखी थी. In case of inception, what we did, we applied 1x1 before 3x3 and 5x5. Later on, 3x3 was asymmetrically converted into 3x1 and 1x3. In inception तो ये तो कर रहा है. स्क्यूज का मतलब ये 1x1 कर दो आप, उससे मल्टीप्लाई करो, just to reduce the number of computations. That's what skews do. Okay, efficient net. Efficient net is a family of again CNN pre-trained models which give high accuracy, which scale. Actually, it's a scaling tech. It performs compound scaling. Efficient net. It increases the depth, it increases the width, it increases the resolution. That's what efficient net do. It arbitrarily increases depth, width, and resolution of a network in a balanced manner. This is called as compound coefficient, compound scaling. Obviously, there is a maths behind it, but I just introducing all these pre-trained architectures. Okay, I use attention mechanism with efficient net. I'm not successful. uh, I haven't tried with this thing like skews net. Okay, but in inception v3 we are having such kind of funda, so I got success with that, it with attention. Densenet I applied at one place, but I haven't got that much success with densenet also, with attention mechanism. Okay, because those which are using skip connection, their attention mechanism, multi-head attention, I haven't got success. ResNet also I failed. I only got success with MobileNet, Inception, Exception, V16 and V19. Okay, so this is like your efficient net, which increases the number of layers, number of channel, number of, that means input size image resolution. Okay, graph convolution network. Graph convolution is designed to handle graph structure. That means where data points are independent, they are base connected with the network like social media. This is graph convolution. वी आर हैविंग वर्टाइसेस एंड द एज, ग्राफ में ये तो होता है, वर्टेक्स एंड द एज होती है। अभी हमारा इशू नहीं है इससे, ग्राफ से। ट्रांसफार्मर में अटेंशन इफ आई एम यूजिंग, तो समझ लो ट्रांसफार्मर लगा दिया मैंने। ट्रांसफार्मर आई थिंक ऑन द मैसेज ना, आई हैव बीन टोल्ड सर ये ट्रांसफार्मर, ग्राफ कन्वोल्यूशन और सर स्क्यूज नेट, एफिशिएंट नेट, सर जस्ट काइंडली थोड़ा सा डिस्क्राइब करो। मैं बता, वही तो बता रहा हूँ। ट्रांसफार्मर का आई जस्ट टेक अ कंपोनेंट ऑफ अटेंशन मैकेनिज्म, आई ऑलरेडी अप्लाइंग अटेंशन मैकेनिज्म ऑन माई इमेजेस। तो बाकी की चीज़ों की जरूरत नहीं, सेल्फ अटेंशन यू नो, स्पेशल अटेंशन यू नो, चैनल अटेंशन यू नो, तो मल्टी, वी आर ऑलरेडी यूजिंग मल्टी हेड अटेंशन। तो मल्टी हेड में इफ यू टेक एट हेड्स, सो ईच एंड एवरी हेड इज डूइंग सम डिफरेंट टास्क, someone is doing spatial, someone is doing self, someone is doing like uh, channel, so dot dot dot, there are so many attention they are applying, so multi head लगा के हमको फायदा हो गया। Okay, multi-head attention. Instead of using single attention mechanism, transformer apply multiple attention head with different aspects. That's what we are doing. ये words के लिए था, अपन image के लिए कर रहे हैं। Okay, कर ही दिया है सब। Then I have been also asked the segmentation के बारे में भी थोड़ा बताइए। Please do tell about the segmentation. तो segmentation, what do you mean by segment? Segmentation में you are going to segment या collection या cluster. In case of machine learning, we say clustering. With this images ना, we say segmentation. सेगमेंटेशन में वो पिक्सल्स कलेक्ट कर रहे हैं अपन, पिक्सल्स होते हैं। ओके, सो इन कंप्यूटर विजन देयर इज अ टास्क दैट पार्टीशन इमेजेस इनटू सेगमेंट। सेगमेंट अब जो होगा, डिवाइड सेगमेंट सेट ऑफ पिक्सल, है ना, वही पिक्सल कलेक्ट कर रहे हैं, ये बोला था मैंने, पिक्सल्स, टू सिंप्लीफाई द रिप्रेजेंटेशन ऑफ एन इमेज एंड मेक इट मोर मीनिंगफुल फॉर एनालिसिस। सेगमेंट इज टू डिवाइड एन इमेज इनटू डिफरेंट रीजन, हाँ रीजन वाली बात है, डिफरेंट रीजन्स। वी आर हैविंग सिमेंटिक सेगमेंटेशन, वी आर हैविंग इंस्टेंस सेगमेंटेशन। वो यहाँ लिखा नहीं है, इट्स नॉट रिटन हियर, आई एम टेलिंग फ्रॉम माई साइड। वी आर हैविंग टू टाइप्स ऑफ सेगमेंटेशन, वन इज सिमेंटिक, अनदर इज इंस्टेंस। सिमेंटिक सेगमेंटेशन में क्या होता है, ये पूरा पिक्सल बेस्ड है, पिक्सल्स। ओके, वी आर कलेक्टिंग द सेट ऑफ पिक्सल्स। इंस्टेंस सेगमेंटेशन में, for example, if there is an image, you are having apple, you are having apple, you are having banana, okay, and you are having any other fruit. So instant segmentation will classify them also. This is apple 1, this is apple 2, this is banana 1, this is banana 2. But in semantic segmentation, it will not classify. It will classify only different objects like apple and banana. It will not further understand that this is apple 1, this is apple 2. No, but this thing is happen in instant segmentation, मतलब ऑब्जेक्ट को भी वो सेगमेंट कर देगा, एप्पल 1 एप्पल 2, बनाना 1 बनाना 2। So just collection of the pixels, dividing the images into segments. That's what we do in case of segmentation. Okay, fine. So yes, you can use skin cancer data set, you can use any kind of data set for your purpose to perform your task, no worry. Okay, so image segmentation can be performed by CNN also. We can perform image segmentation by CNN. Okay, by fully connected layer, we can perform segmentation. These are the algorithms which we can use to perform segmentation. Like fully convolution network, we can use unit. This is famous architecture. Unit. It is a well-known architecture used for image segmentation, particularly in medical image. Especially if you are working on segmentation, unit. I think I have made one project on teeth segmentation. There I have used unit only. It is having encoder or decoder. Okay, the left side of the U reduces spatial, the right side of the U upsample. So in convolution also we are having upsampling and the downsampling. In general, we do downsampling. If you are using convolution 2D, you are performing downsampling. That means you are reducing the number of features. That means you are extracting the feature, reducing the size. We are having upsampling also. Upsampling is called as inverse convolution. That is transpose of convolution, where you increase the number of size of the data. That is ट्रांसपोज. तो ये चीज होती है ना, वो एनकोडर डिकोडर में होती है. एनकोडर अप डाउन सैंपल करता है, डिकोडर अप सैंपल करता है. Encoder reduces the size, decoder increases the size. Okay, so this is the architecture which we use in unit. We take image of this size, we perform convolution, then we capture the features, and then we again upsample, and this is what we do produce, segmented result we do produce. So especially used in MRI, medical imaging. Okay, semantic segmentation for autonomous driving vehicle we use. There are other architectures also like SegNet, then Deep Lab. Okay, many architectures are there. Mass RCNN. So now later on, this CNN has been we do use this YOLO versions. ठीक है, YOLO वर्जन यूज करने लग गए अपन. तो आप YOLO से भी कॉन्सेप्ट ले सकते हो. You only look once. For example, आपको उन architectures को भी go through. Those people who are working in medical imaging, those who are working with the images, भाई मैंडेटरी है, आपको तो सारे थरो होना चाहिए. ऑल द आर्किटेक्चर शुड बी थरो. देन फिर आपको देखिए, मैं आपको अप्रोच बता रहा हूँ. इफ यू आर डूइंग अ PhD पर्सन और वॉट एवर, ओके, सो यू हैव टू मेक अ प्रॉपर नोट्स. ओके, यू शुड बी हैविंग एन आर्किटेक्चर. ओके, आर्किटेक्चर होगा आपके पास. देन दिस आर्किटेक्चर, नेम ऑफ द आर्किटेक्चर, नंबर ऑफ लेयर्स यूज्ड. ओके, मैकेनिज्म क्या है, व्हाट इज द मैकेनिज्म. ओके, एंड इसका प्लस पॉइंट एंड माइनस पॉइंट क्या है. देन अगेन आर्किटेक्चर, लेयर्स, मैकेनिज्म क्या है, प्लस पॉइंट माइनस पॉइंट क्या है. all these like architectures you have to note it down. सब करना है पूरा. नॉट बिग डील, आप बना सकते हो, रिसोर्सेज अवेलेबल है. ओके, तो ये जो ड्रॉबैक्स हैं, हाउ दे कैन बी इम्प्रूव, इस पर फोकस करके, इसका ड्रॉबैक, इसका फायदा है क्या. दिस ड्रॉबैक, वेल दिस इज द, ये ऐसा क्रॉस हो सकता है क्या. Okay, so pick any of one which you are interested in, you want to improve. Pick any of the one which you want to improve. Try to incorporate some more layers, some mechanisms, some technique, and just try to test on your data. And you write the entire maths for it, because I know you have to publish in some good journals. Write the maths for it. That अब क्या maths, what kind of maths they did, they reduce the computation, they increases the score. आपको भी यही करना है. And you have to test your model on different data. This is the score, this is the score, this is the score, this is the score. Our model got good score, your paper published. Okay, and here it is. एक मैं और भी है मेरे पास कोड, ये रहा मेरा कोड फॉर सेगमेंटेशन. Here I perform the segmentation with simple convolution. Very simple convolution pooling. Then I perform inverse like transpose convolution, and ये रहा मेरा segmented image. I took chest X-ray only. This is segmented image, not looking good. But after that, I use UNet model, UNet architecture. This is a better architecture. First, I perform downsampling, that is encoder. Convolution, convolution, pooling, convolution, convolution, pooling, convolution, convolution, pooling. यानी इमेज का साइज छोटा 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 छोटा, small small small, do it small. Then this is bottleneck layer. This is bottleneck. Convolution 2D, 512, 512. This is bottleneck. Okay, and then this is decoder, upsampling. Now you need to increase the size. This is upsampling. Okay, and finally, I got the segmented result. I loaded the chest X-ray again. This is what I got. This is segmented image. So unit, if the question asked to me, sir, kindly tell about the segmentation also. So unit is an architecture which you have to go through for segmentation. Okay, got it. I think that is what I need to speak. Yeah. Anything you guys want to speak, please you can. Okay, I do have a code related to like this for separable convolution also. This is a code for separable convolution. Okay, let me increase the size and show you. I have made all these codes and I will share it to you also. Depthwise convolution, separable. Okay, so there is already depthwise convolution layer available, already available. You just use depthwise convolution in your code and it will work. Okay. Yes, please ask the question.
Yes, sir. This is an excellent lecture. Thank you. I posted a question about I'm considering increasing efficiency by focusing on the stride component using an adaptive stride selection where depending on the information density of the image, it takes larger strides or smaller strides. And I'm wondering if you think that that's a feasible component to add to an architecture and how that might be done.
Yes, a stride, as what we have studied, is how many pixels we do jump. If we want to reduce the size of the image, then sir, we do take higher stride. Okay, sir. So if the size of the image is big, for example, sometimes we do have so enlarged images in medical, enlarged, very enlarged images. So, sir, in that particular case, you can take higher stride. So the reduction in the size of the image will be there. In case as we are already performing the reshape of the image into 224 or 299, so there in that particular case, sir, stride 22 is fine, sir. Striding 22
I'm,
is fine
I'm
or 11 is fine.
I'm thinking of, so in that case, what you just described is a fixed stride depending on the resolution, and I'm considering more of a dynamic stride adaptation where in the same image, the same resolution, areas where there's low information density towards the outer regions where it's black, the stride would adjust with larger segments
Okay.
until it hits a feature, in which case it would go smaller, which would increase the efficiency.
Yes, sir, that is a good suggestion. And sir, for the border areas, we are performing, sir, padding. Padding equal to same. And sir, we are filling that with zeros. That mechanism, na, for the border areas, they told you do padding. So then, while performing striding, there will not be any issue. In convolution, sir, we are doing padding. So, sir, that issue na is been met by this phenomena. Rest they are keeping the striding same 2 2. Okay, sir. And the meaning of the striding is just like we how much information we want to take from the image. Okay, if we keep dynamic striding somewhere 1 1, somewhere 2 2, okay, something like that, sir, we can try. We can
How,
definitely try.
how would that be done? Can you just describe how you might do a dynamic striding?
So dynamic striding, we can as we did with convolution asymmetric, something like that. Okay, so 2 cross 1, 1 cross 2. However, it should cover or capture the entire image. That's
Yeah.
something important, sir. Okay, that's
Mhm.
something important. So
Okay.
either you have to fix the resolution accordingly, what needs to be kept. Okay, and sir, because our image is having border, our image is having center regions, our image is having all the regions. So convolution is totally based upon feature extraction. We don't want to skip anything which is present at the border, which is present at the center. That is how we have to think about the striding. So they keep that, okay, let's stride by 2 2, or let's stride by one striding you can do. So at least you will capture each and everything. Okay, that's why they kept it fixed. But right now, sir, you are saying that, okay, can we make as a dynamic? Sir, I never deny anything in artificial intelligence. I never deny
Hmm.
anything. Everything is possible, sir. If any question come to
Yes.
me, sir, is this possible? I will say yes. Let's try. Because denial of anything is just a mistake. Now
I have
everything is
another
possible.
question.
Yeah, sir, please say.
So I have asked a few questions in the past about the possibility of reducing with grayscale images in order to increase efficiency, only considering one channel.
Huh.
I'm also wondering, and what you told me was that with pre-trained models, they assume RGB, so we have to basically add 3 layers.
Yes, sir.
And so
Actually,
that adds a level of inefficiency. But if we were training our own models, we could use a single layer. What I'm also wondering though is would it be possible to take an RGB image and just like with augmentation, run each channel through like a red channel, green channel, blue channel as separate images and train on them separately to gain some efficiency. So you wouldn't have necessarily 3 times the well. I don't know if you follow what I'm
yes, sir.
saying, but
Yes, sir. Yes, sir. I
if
got it. And
you
sir, we
train
have
with those separate channels.
sir, in separable convolution, that's what the technique we are applying, no, sir. Separable convolution, that's what we did with different channels, red channel, green channel, blue channel. Okay, we did applied what depthwise convolution here separately. Okay, you are also saying that it's better that if you are having a colored image, let's separate the channels and then apply training over these channels separately.
Yeah,
Okay, rather
yeah.
than doing all in a one, it is increasing the computational complexity. They are saying that, okay, we will do this thing. Okay, you want to separate now, you want to separate the image, you can do that. You can do that with depthwise convolution, you can do that. And that's what we have learned in case of exception.
Mhm.
Okay, you can do that. Separate the image on the basis of channels, apply filter on it. By doing
Yeah.
independently also you are going to do the same. Apply filter over it independently. Okay, whatever be the result you are getting, then next you are applying 1 cross 1. Or either they told that apply first 1 cross 1, that is pointwise, and then apply filter, this depthwise in exception. That's what they are saying. First do this thing, reduce the size, and then apply depthwise.
Okay.
Okay,
The
so
reason I'm asking about this is because of MobileNet. I'm trying to come up with a lightweight
okay, yes, sir.
neural network that can be run on mobile, and I'm thinking most of the information on images is captured on grayscale, honestly.
Yeah.
So we don't really need all those channels except in very, very specific circumstances. Is it possible to get some hybrid between having all 3 channels and purely grayscale by just sampling more sampling the different channels for a lightweight architecture?
Yes, sir, it is possible, and we can perform this task. Like we can separate the image over, for example, 3 channels. We can apply our technique over it, and then, sir, later on we can combine the results. We can perform the concatenation of this result. Okay, so separately we can train, and whatever be the results, we can combine or concatenate. This is possible. That we can take the inspiration from depthwise separable only. That's what we can do.
Okay, thank you.
All right, all right, all right.
Hello, sir.
Yes, please. Sir.
Sir, if say in our research work, if say we are going to modify the architecture,